Okay, so this work is on the adaptive gradient methods with local guarantees. I'm Joe, and this is joint work with Wenhan, Sanjeev, and Elad. So in short, we propose a new algorithm called Samuel, and in theory, it achieves the improved adaptive grade bound, and in practice, we apply it to learning rate schedule in optimization. Okay, so let's go on. So we consider the online convex optimization problem. Okay, so we probably contain more contents in the text than the talk, so I will skip much of them. So the base setting is at each round T, the player makes a decision and the nature adversarially chose a loss function, and the goal is to minimize the grade. That's the loss suffered by the player minus the loss of the best fixed action in all the comparative in hindsight. However, this regret metric is defined for the whole interval 1 to t, and in changing environments, it may make more sense to consider it locally. So we have an alternate metric called adaptive grade, which has an additional variable I, which denotes the length of the any subinterval, and the adaptive grade is defined to be like the the worst interval with length I, the grade of that interval. Okay. So however, we have a gap between these grade bounds in different settings. So for general grade, we know currently the optimal method is adequate, theoretically, which achieves a full matrix second order grade bound. But for adaptive grade, we simply have this square root I like grade bound. It's like the bound of gradient descent. So the question is, can we achieve the improved full matrix bound for adaptive grade? So in this paper, we propose an algorithm Samuel that also achieves the optimal full matrix grade bound, but for any interval, any subinterval of 1 to t simultaneous. So it's like achieve the best of both worlds. So the technical challenge was that for to achieve the optimal bound, we need to decide the eta in the multiply weight algorithm in advance optimally, but this eta will depend on future gradient information which you don't know in advance. So our solution is to construct a candidate set of many etas so that one of them is guaranteed to be optimal, and we make duplicates of many experts for different etas, so the multiply weight can also select the best eta. Yeah. So algorithm looks like this. First, we define a set of intervals called geometric intervals, which is a subset of the power, all the possible set of intervals. Then for each interval, we construct an instance of expert algorithm, say AdGrad, and then we run a variant of multiple weight algorithm on top of these experts. And each episode, we make duplicates of them, with different etas in the multiple weight part. Okay, so now comes to the application. So, the challenges in deep learning training, one of them is the learning rate schedule, because to achieving SOTA, you really need to depend on the optimal choice of learning rate. But constant learning rate is apparently not optimal, and there's no gold standard for choosing learning rate. And we can see this problem as a changing environment because the loss landscape changes over time. So that's why we can apply our algorithm. Yeah. So why our algorithm is useful? Because the landscape is changing and it's complicated, and different stages of optimization requires different learning rates. So we just first we choose optimal optimization algorithm, say AdGrad, and we choose a set of learning rate schedules, and then we treat these expert algorithms as experts, and we feed them into our algorithm Samuel. So this is the result for the image classification. So this is CIFAR 10. So the figure on top is the results for the brute force like uh, linear rate schedulers, and the bottom is like the performance of our algorithm, and you can see that our algorithm nearly matches the best of the all the possible brute force linear schedules, so it's near optimal. So similar results for ImageNet. And here the setting is a little different. So at different stages, like the candidate set of learning rates are actually decreasing. So that's more practical. And also language task results. So in the end, we have also shown the stability of our algorithm. That's like the hyperparameter tuning doesn't really matter in our algorithm. So it's very stable and robust and doesn't need like much of tuning. So conclusion is we developed a method called Semele that can, like in practice, automatically select learning rate on the fly, and it is stable and it's accessible and robust. Okay, thank you.